Knowing that logarithms and exponentials are inverses of each other, then we can apply the same knowledge that we had from our original study of inverse functions to the graphs of these two functions here. So we have y equals e to the x, so we're using that natural base e for our exponential, which then means for the inverse function, we're going to have the natural log, so the log base e of x. So remember that the graphs are reflections of each other across the line y equals x. So let's start with the familiar, the graph of y equals e to the x, an exponential function, and then we'll just flip-flop the x and y coordinates and see what that generates for our logarithmic graph. So we'll go in blue here for the exponential. So we can plug in a few points to kind of help us out. So if I plug in 0 for x, I'm going to get 1. We know that that's the default y-intercept for an exponential function with no dilation factor. If I plug in 1 for x, we get e to the first, which is just e, which is 2.7-ish. So I'm over 1, up a little bit short of 3. And so from there, our graph is going to continue to increase. And then as we go in the negative direction, we're getting closer and closer to the x-axis. Recall that we have a horizontal asymptote at the line y equals 0. So we have y equals 0 as our asymptote. We have a y-intercept at 0, 1. And then, of course, our domain is all real numbers, as it is for any exponential function. So if we didn't plug in any numbers, we could still generate the graph of the natural log of x just by knowing that it's the inverse of e to the x, and therefore it's just the reversal of all of our x and y coordinates. So if the exponential graph goes through 0, 1, our graph for the log of x, natural log of x, is going to be go through 1, 0. We're going to have an x-intercept at 1, 0. If we have an asymptote of y equals 0 for the exponential, flip-flopping x and y means that x equals 0 is going to be our vertical asymptote. So we're going to have a vertical asymptote here. And then if we take the natural log of e, so if we want to plug in a point to help us out, so if we plug in e for x, again, that means our input is 2.7-ish. So our output then would be 1, because when the base of the log and the input into the log match, the answer is always 1. And so that would correspond with the point that we had on our exponential curve when we plugged in 1 for x and we got e as the output. Now if we plug in e as the input, we're going to get 1 as the output. So I'm going to have a point roughly right about there. And so then our graph is going to look something like this. And so if we tilt our head sideways, the blue line and the purple line are indeed reflections of each other across that line, y equals x. All of our inputs and outputs have been flip-flopped to end up generating this graph. So just like almost every exponential function, barring some kind of translations or reflections or anything like that, has the shape of our blue line here, where it's going to be approaching a horizontal asymptote along the x-axis as we go farther and farther to the left, and it's going to increase to infinity as we move farther and farther to the right. So that's the standard shape for an exponential function. Same thing is true for a logarithmic function. Our default for a logarithmic function is going to be to have a vertical asymptote along the line of the y-axis, x equals 0. We're going to end up with a graph that is going to go down to negative infinity as we get closer and closer to 0 being the input. And then we're going to have this kind of slowing rate of increase as we move across the graph from left to right. And so our domain for a logarithmic function is going to be x is greater than 0. And if we think about that from the context of some of the other work that we've done, we can't plug in 0 into a logarithm. We can't plug in a negative number. So the only numbers we're allowed to plug in are positives, so x has to be greater than 0. And so just like we saw with the exponential functions, we can have translations, dilations, and reflections applied to these logarithmic functions. Again, we're not going to see lots of these, but we should be familiar with them at least a little bit. So I encourage you to graph these on your graphing calculator after we're done to kind of double check and get that practice. And a good place to start would be perhaps to just graph y equals the log base 2 of x. So ignore the negative that's out front, the minus 3 that's on the inside, piece this graph together, and then see how the reflections in the x-axis and the translation of negative 3 will be, of 3 in the horizontal direction will impact our graph. So for just log base 2 of x, our standard logarithmic function is going to have, and I'll do this one in black, is going to have an asymptote along the y-axis. We're going to go through the point 1, 0, and then we're going to go through the point 2, 1. So whatever the base is, 1 is going to be a standard point that our graph goes through. So armed with those two, we can get a general sketch of our graph. So we're going to approach that vertical asymptote, get closer and closer to it as we go farther and farther down. And then we have this kind of slowing growth as we move to the right. So investigating the two transformations that we have here, we have the negative out front. So we're going to have a reflection across the x-axis. As a result of that, all of our inputs end up opposites. So if that was the only thing that was happening, we would just reflect across the x-axis, so we'd end up with a shape that looks like this. But that's not the only thing that we have happening, so I'm going to undo that there. We also have this minus 3 on the inside, so that means we have a horizontal translation, so we're translated, and then it's the opposite of the positive negative sign that we would expect. So we're translated 3 units to the right. So that means everything is going to move 3 units that direction. So that means our asymptote is going to move, everything's going to move. So we'll go ahead and move that over in blue here. So we'll have a vertical asymptote now at 3. So at x equals 3. Our intercept is going to move as well. So we're going to have an x-intercept at 4, 0 instead of at 1, 0. And then again, because of the reflection, we're going to be with this graph that's going to look like this. So we're reflecting that black graph across the x-axis, so it's going to be upside down from what we see, with the translation to the right as well. And so our domain now, remember, you can't take the log of 0, you can't take the log of a negative. So the easy way to determine the domain would be to take whatever's inside of the logarithm and just set it greater than 0 and solve. But we can see from the asymptote, the domain is going to be x is greater than 3. This is just an example of how we can apply some of our transformations. Again, we won't see too many graphs involving transformations with these logarithmic functions, but we need to be familiar with the fact that they can be present, and so we want to go through an example that showed that.